Let's revisit an example we talked about at the beginning of the course, which was the free expansion of an ideal gas. And so in this example, we had a rigid compartment that was well insulated, and the vessel was split into two subcompartments. On the left-hand side, we had a gas, and on the right-hand side, we had a compartment that was just completely empty. So it was a complete vacuum. There's nothing in there. A wall separated the two compartments initially, but then at some point, that wall is removed. Either like a hole is poked into it, or the wall is just slid out of the way. In any case, because this wall is moved out of the way, that allows the gas to then expand to fill up the entire vessel. We did an energy balance analysis on this free expansion. And from our energy balance, we showed that the change in internal energy of the system was equal to 0. Q is equal to 0 because the vessel is well insulated, so it's adiabatic. But work is also equal to 0. Even though the gas is expanding, because it's expanding against the vacuum, that means there's no opposite force acting against its expansion. Okay, and so because that opposite force is equal to 0, that means that work is also equal to 0 as well. And so we showed that delta U is equal to 0 for this free expansion. Therefore, the internal energy at state 1 is equal to the internal energy at state 2. For the ideal gas, the internal energy is only a function of temperature. And so that means that the temperature in state 1 was equal to the temperature in state 2 after the gas expands. And so this process is also isothermal. And so this is what we learned from the energy balance analysis. But what we didn't do back then is we didn't do the entropy balance analysis. So let's do that now. So from our entropy balance for a closed system, we could start with a difference form. Delta S is equal to the summations of any Q's over temperatures plus entropy generated. This is an adiabatic system, so the Q's are equal to 0. And so what we get is that delta S is just equal to S gen. To figure out delta S, we could write it in terms of the molar entropy. And to figure out the change in molar entropy, we could just apply the fundamental entropy equation. V2. Okay? This process, as we showed from the energy balance, is isothermal. So this first term goes away. And if we just carry out the integration on the volume derivative, or the volume integral, we get that the delta S is just equal to nR natural log of the molar volume 2 over the molar volume 1. Here, if we take a look, the number of moles is the same in both state 1 and state 2, but the volume in state 2 is bigger than the volume in state 1. Molar volume is volume over moles, therefore molar volume 2 is bigger than molar volume 1. And so if that ratio is greater than 1, that means that the natural log is positive, and so our delta S is also positive. And so delta S is equal to S gen. Delta S is positive. That means that S gen is also positive as well. And so if S gen is positive, that means what we're dealing with is a spontaneous and irreversible process. So this free expansion happens spontaneously, and it's an irreversible process. Okay? And so that's what we show from the entropy balance, right? That, if we poke a hole in that wall, the gas will spontaneously just expand to fill up both compartments. That's what the math tells us. But at least to get a more kind of physical understanding of what's going on, we could also think about what's happening microscopically. Right? To do that, let's think about the base definition of entropy, which is just the number of ways that molecules can arrange themselves in a system. Right? And so, we see from our math that delta S increases. And that's because if we increase the available volume for the gas, right, that means that there's more places that the gas molecules can be. And if there's more places that the gas molecules can be, that means that there's going to be more ways that they can arrange themselves, more places that they could possibly be. Right? And so delta S increases because molecules have more ways that they can arrange themselves. So an individual gas molecule, after it expands, or before it expands, it could only be, here on the left-hand side. But after the wall is removed, a gas molecule could be here, or it could be here, or it could be here, 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 here. Right? It has more places that it could possibly be. And so that's why the delta S increases. And so, through this free expansion system, we see that, once we remove that wall, the gas moves towards a state in which its entropy increases. But in general, the observations we see from this example are actually pretty general. Right? And so in general, if we're dealing with an isolated system, what we see is that isolated systems will spontaneously and irreversibly move towards a state that increases their entropy. Okay? Right? And so, we see this in the expansion of a gas. So gases expanding to larger volumes. But we also see this in other types of systems. So if you think about your transport class, where you talk about fluid flow, what you typically see is that fluids move from areas where they're at high pressure, they move to areas where they're at lower pressure, right? And we saw that entropy entropy increases as you decrease pressure, right? And so a fluid moves to an area of lower pressure because that will increase its entropy. Also, in your transport class, you're probably talking a lot about heat transfer now, right? So heat transfer through walls, where one side of the wall is hot and one side of the wall is cold. And you see that heat will flow only from the hot side to the cold side. So from high T to low T, right? And we see that because the lower temperature part of the wall, as heat flows to it, that lower temperature part of the wall will get hotter, right? And as the lower temperature part of the wall gets hotter, its entropy also increases, okay? All right, and so we see that for these isolated systems, that they move towards states that increase their entropy. But eventually, if we wait long enough, so if we wait an infinite amount of time, we'll see that these systems will stop evolving. With a free expansion, eventually the gas moves and fills up the entire vessel, right? And once it does that, then that's it. The gas can't expand anymore. Or, with the example of heat flow, heat will flow from the hot side to the cold side until both sides are the same temperature, right? And then at that point, heat will stop flowing. All right, and so that's what we observe in real life, right? We observe that our chemical systems, will move towards a state that increases their entropy until, they can't change anymore, right? Until that entropy reaches the highest value that it can. And so based on this observation, we can make a hypothesis, right? And so when these systems stop evolving, we say that they're equilibrated, or that they've reached equilibrium, right? And so our hypothesis is going to be that the equilibrium of an isolated system, so isolated, we're going to say that's equilibrium state is the state in which the system has reached a maximum entropy. Okay? All right, and so that is our hypothesis about, why systems behave the way they do, why they move towards states that increase their entropy, and then once they reach a state of maximum entropy, why they don't change anymore, right? And so we're going to say that equilibrium is going to be the state in which the system has maxed out its entropy.